The other reducing agent we can use is hydrogen, and you'll see from the top of the next page that the metal that we use to use hydrogen to extract is tungsten. Now, tungsten isn't used as much nowadays as it used to be because the place it's used or was used quite a bit, light bulb filaments, and filament light bulbs are certainly being phased out quite a bit, and electrical bar heaters, which again are the most efficient heaters and therefore are used less and less frequently nowadays. When they are used, basically what happens is the tungsten is heated up, it gives out light and heat, and that's the reason we use it. Now, to remember the equation, first of all, you'll see the tungsten oxide reduction equation here. And tungsten oxide, tungsten is tungsten 6 oxide. So as you'll see from up here, tungsten is plus 6, oxide is minus 2, so WO3. Because it needs the 3 oxygens removed, need 3 hydrogens to react with it, that gives us tungsten and 3 water. And that process is quite good because the water is a gas at the high temperatures used here, and therefore very easily given off, and it leaves behind a pure product. There is a risk, obviously. Hydrogen's explosive, it's flammable gas, explosive, and therefore there's always a risk of fire or explosion when using it. The next example of reducing of a metal is using a reactive metal to do it. The example again that we use here is titanium, and titanium is used for quite high spec requirements, so things like anything that requires lightness and strength, so aircraft or high spec bicycle frames, so for example the type that the Olympic riders use will quite often have a high percentage of titanium in it. 2 processes to extract it, and the first thing is that we start off with titanium 4 oxide, so again note it's plus 4, we'll come back to why that's important shortly, and this is titanium plus 4 there. And the 4 oxide, titanium 4 oxide, TiO2, is turned into titanium chloride, TiCl4. To do that, we require carbon and chlorine. Now, don't forget about the carbon. You'll see that when it comes to exam questions, you're sometimes asked to write those, and that's a common mistake, is to forget the carbon. So, titanium 4 oxide, TiO2, plus carbon plus chlorine gives us titanium chloride and carbon monoxide. The titanium chloride has to be kept separate from water because it'll hydrolyze, but if we do it in an inert atmosphere of argon, we can extract it, or we can purify it by fractional distillation, and therefore the titanium that we extract is quite pure. Then, once we've got our titanium chloride, TiCl4, to reduce it, we use sodium, and you can see because the sodium ends up as plus 1, we need 4 sodiums to react with titanium chloride, and that gives us 4 NaCl and then the titanium. The conditions needed, this requires an inert atmosphere of a noble gas, so for example argon again. Now, again, the reason for this is the sodium obviously is a very reactive substance, and we want to make sure that there's no potential explosions or anything. The reaction is exothermic, and you'll see there that the temperature usually starts about 500 and goes up to about 1000. The main impurity in this, sodium chloride, and then to remove that, basically is mixed with water, and then the titanium is left behind. So the titanium is insoluble, sodium chloride is soluble, so that's why water will separate the two. This is soluble and can be dissolved away, and then the titanium, which is insoluble, can be filtered off. Now, in other parts of the world, they use magnesium to reduce the titanium chloride. Now, the reason this works is magnesium is higher up the reactivity than titanium, so again it can steal away the chlorine, so it becomes magnesium chloride and titanium. As you can see from the equation that I've written there, the magnesium is plus 2, so therefore I get MgCl2. That means we only need 2 magnesiums to steal away the 4 chlorines, and then that leaves the titanium in the same way. Now, you can list down here in your notes why titanium is going to be an expensive metal, and if you go back to the process and try and kind of summarise what we've done there, look at all that has to happen to extract the titanium. We have to react it with chlorine, which is expensive. Chlorine's a chemical that has to be extracted by electrolysis, so it's an expensive chemical. We've got carbon reacting with it, so we've got a whole processing there. We then also have to carry out fractional distillation, so expensive reagent chlorine, expensive processing, fractional distillation being carried out. Then when we come to the reduction stage, again we've got specialist apparatus needed, specialist equipment needed, because the sodium is so reactive it could react with the air, so we have to ensure that's excluded. And again we've got another expensive reagent there, sodium, and sodium is basically an expensive reagent because it has to be extracted by electrolysis using electricity, so therefore it's going to be expensive. So you've a lot of processing, you've a lot of expensive reagents, you've got specialist apparatus. All of that leads to titanium being a very expensive metal. So it's only used for high spec work, so racing bicycles or aircraft, something like that, or it can be used in things like spare parts surgery. For example, brain plates are made out of titanium, or parts of joints that are being replaced. So it's where you need a very, very high grade metal, and that's where we use titanium. The next reduction to look at is electrolysis, and the example of electrolysis that we use is the extraction of aluminium oxide. And you can see with this one, this is very similar to what we had at GCSE, so it's going to be a quick race through to show this. So first of all, the extraction of aluminium oxide uses, or the extraction of aluminium is from aluminium oxide, which is in bauxite. Now bauxite is a slight pinky coloured ore, and the reason for that is that aluminium oxide, that the main chemical that's in it, Al2O3, is mixed with a little bit of iron 3 oxides. Remember that from our extraction of iron, rust, so it's a reddy colour, and then some sand, silicon dioxide. Now it means then that we have to first of all extract the aluminium oxide before we carry out our electrolysis. So if you look at this stage, a quick read over this and know the outline of the purification of bauxite. So bauxite, we said, is these three mixed together: aluminium oxide, iron oxide and silicon dioxide. So what we do is we first of all mix the ore bauxite with sodium hydroxide. And why sodium hydroxide? Well, aluminium oxide is what's called amphoteric. It'll dissolve in acidic solutions but also alkaline solutions, and it dissolves to give us the aluminate ion. So at this stage, that's all you have to remember: it dissolves to give us this aluminate ion. So it's soluble. But under the conditions that are used, silicon dioxide and iron oxide don't dissolve. They won't dissolve in the sodium hydroxide. So this is soluble, this is insoluble. So therefore, to get rid of it, we filter. And if we filter it off, the silicon dioxide and iron oxide get trapped, and that means that the aluminium, as in the form of aluminate ion, will pass through. The aluminate is then basically precipitated, has aluminium hydroxide precipitated out of it, using alkaline solution and so on, and heating it, and then it's basically dried to give pure aluminium oxide. And in the industry, that's commonly called alumina. So aluminium oxide or alumina. Now, the electrolysis is then of this aluminium oxide. So there's our electrolysis cell, which you may remember from GCSE. So again, refamiliarize yourself with that diagram. So the carbon anodes, so carbon dips into it, and then that anode means it's positively charged. The mixture will come to in a moment. The steel outline there, you'll see this sort of steel container that it's in, and then that's lined again with carbon that's attached to the negative supply. So there, the cathode. So we've got an anode and a cathode, and then the electrolyte is aluminium oxide in a substance called cryolite. Now you'll see shortly below, cryolite is a fluoride compound, but if you dissolve the aluminium oxide in it, rather than having over 2000 degrees centigrade, which is normally required to melt pure aluminium oxide, the whole mixture really melts at about 950 degrees centigrade, a much, much lower melting point. So effectively what the cryolite does is it lowers the melting point. It has another purpose as well. It means the electrical conductivity is better, and therefore the extraction is much more efficient. The whole process is carried out and the aluminium is produced at the cathode. So again, look, we've got a reduction reaction here. So there's one of our half equations that we saw when we did our redox section. So aluminium ions, which are in the aluminium oxide Al3+, they gain 3 electrons, reduction being the gain of electrons, and that gives us aluminium. Meanwhile, at the anode, oxide ions, which are the other ions, they basically lose electrons, they get oxidized, and they're given off as oxygen gas. So O2 minus turns into O2, and to balance that I've used a half in front of it, and 2 electrons given off. So this has lost the electrons, and therefore is oxidation. This is gained electrons and is reduction. So we've reduced the aluminium ions to aluminium. Now, an offshoot of that is that the anode, oxygen is passing over the anode. The anode, you remember, were made out of carbon. So therefore the carbon, the oxygen can react. There's a couple of equations to show how they could potentially react. They either give off carbon monoxide or carbon dioxide. That's again a potentially environmental problem, carbon dioxide gas being given off. The other potential environmental problem with this is the cryolite is a fluoride compound, and we have to be a little bit careful with fluoride compounds because fluoride compounds leaked into the environment can cause fluoridosis, and fluoridosis is basically a medical condition that damages bones and teeth and so on, although it needs quite high percentages of it for that to happen. So we do have to be environmentally aware with this again. And then the final page, and don't ignore this page because this is quite important, these are the environmental aspects. So, as we've seen, metal extraction has the potential to produce large quantities of gases that can cause, for example, acid rain. So, do you remember which gas? Sulfur dioxide, that's right. So, from the roasting of sulfides. So, SO2, if I can get this to right, SO2. It causes the increase in carbon dioxide layers, and I'll not take time and write out, you can list them off. So which processes lead to an increase in carbon dioxide levels? Well, look back in the notes if you want. The processes, you remember, are the blast furnace, the extraction of iron from the blast furnace. Also where we extract other metals with carbon, so copper was extracted with carbon, and that led to carbon dioxide. Manganese is extracted with carbon, and then even the last one we looked at there, the extraction of aluminium from electrolysis, because of the carbon that wears away at the anode with the oxygen given as carbon dioxide. The global problem that causes, remember, is buildup of carbon dioxide, and therefore is thought to be contributing towards global warming. We seem to be increasing our amount of carbon dioxide at the moment. The other environmental aspects to look at as well is recycling of metals, and the recycling of metals is a very important process nowadays. It's desirable, obviously, because it means that you're using less resources, and therefore you're still able to have metals, but you're not going and taking the ores from the ground to the same extent. So it seems as if recycling is great. It has no drawbacks from it whatsoever. However, it does still have an environmental impact. So why will reusing these metals have an environmental impact is sometimes asked. And the reason is that if you think of it, once the metals are used, they're not all in the one place. So, and again, you can list these down in your notes. What will happen then is, first thing you have to do is you basically have to gather them. So there's an environmental impact in gathering that. You're going to be burning fossil fuels probably to power lorries, cars, etc. to collect those. When you bring them back, you're going to have some sort of process to sort or to clean them, and that probably is going to use some sort of fossil fuels, so there is an energy requirement there. And then even recycling something like aluminium, which really only requires remelting to reuse it, again, whenever you come to do that with the aluminium, you have to put in energy to gather them, but you also have to put in energy to melt them down and so on. So there still is an environmental impact from that.